Okay, hello everyone. I hope you are doing well and enjoying your last day of classes and studying hard for the final exams, all the final exams that you have. My name is Mitchell Scott. I'm one of the instructors for Math 111, and today we're going to be doing a targeted review session on integration techniques. Um, so as always, this is going to be recorded, and the notes that I'm currently writing on are on the Canvas page under the final exam information. So please feel free to either copy them down, download the file, or just write with me. Depending on when you're watching this, this actually might the Mitchell's integration review notes might be the review notes from today, but as of the time of recording, it is the blank sheet that I have that we're going to be working through together. And I'm going to be posting this recording as well. Um, so yes, let's get started. So really when it comes to integration techniques, we have a few options, right? So we can't forget the original, which is geometric shapes, so rectangles, triangles, trapezoids, so circles, right? But through kind of our anti-differentiation and the first and second fundamental theorem of calculus, we can expand what we can do with integrals to a lot of different classes. And specifically, there's going to be a lot of U substitution problems here because I think if you know how to do U substitution and get it to a simple antiderivative, then that step of taking the antiderivative and checking should be relatively straightforward. Okay, so I say all that. So right now we have our first integral. It's a definite integral, which means that there is going to end up with a finite answer, not a family of antiderivatives. And we are going to solve this, right? So first things first, I'm going to attempt to do this two ways. Okay, so what I'm going to do over here is I'm going to write the integral of rewrite it 125 x plus 21 dx. And the dx is for both of these, right? The whole integrand. Um, with that being said, I see an x to the power 1 here. I can rewrite it as x to the power 1. And I see that there's an x to the power 0 here, or this is a constant, right? So both of these terms, we can do the inverse power rule, right, to find the antiderivative. So I'm going to do that. And remember, constants times functions are much like derivatives, where a constant times a function, if you want to integrate that, that's the same as integrating the function and then multiplying by the constant. So I'm going to do that. So 2.125, and then now we have x to the first. So that's going to become x to the 2. You add 1 to the power and then divide by 2, right? And then the second one is going to be 21 x to the 1, 0 plus 1 equals 1. And then we could divide by 1, but every number is divided by 1, right? And then we don't have to worry about the plus c here because of the fact that it's a definite integral, as we talked about in class. So then we're going to evaluate this at x equals 4 and x equals 0 by the second fundamental theorem of calculus, right? So we get minus 2.125, 4 squared over 2 plus 21 times 4. And then we are going to be subtracting the everything where it's evaluated at 0, right? So we have minus 2.125, 0 squared over 2 plus 21 times 0. And we see that both terms are going to go to 0. So we really have to just simplify this. So this is going to be minus 2.125. 4 squared is 16, but we're then dividing by 2. So that's going to leave us with 8. And then this is going to be 84. And then as I said, 0 times anything is going to be 0. So both of these go to 0 or are 0. So we're going to subtract 0. And we have to do this, if you notice 0.125, that's actually a 1/8 is a fraction, right? So we can rewrite this as minus, right? 8 times 2, that's 16, plus 1/8, that's actually going to be 17, plus 84. And if you do some quick subtraction, you realize that this answer is going to be 6, 7. And we can always check our answer, right? So I'm going to go to gray to check our antiderivative to make sure that this antiderivative right here is actually what we want, right? So since we took the antiderivative and we got this, if we take the derivative, we should hopefully get the integrand back again. So I'm going to do that here. D dx of minus 2.125 x squared over 2 plus 21x, right? So again, we call this process the inverse power rule because when we're taking the derivative, this is just the power rule. So we get minus 2.125 times 2x over 2, and then the second term is just going to be plus 21. So we see that this 2 and this 2 are going to cancel, and we actually end up with exactly the same as the integrand, so we know that we correctly took the antiderivative. Now what I'm going to do though is if you recognize, right, if for whatever reason you forget the power rule here, you could recognize that this is a line, right? At the end of the day, this is a line, and we know what lines look like. In fact, if we were to graph this function, if we were to graph this function, right, where this is x and this is f of x, right? If x equals 0 here, right, then we know that this goes to 21. And then if x equals 4 here, right, make our axes, right, we would just have to plug in times 4 plus 21. And this is actually going to be 12.5, right? So we know that the height at this point is going to be 12.5 and that this is just a line, right? And so really what this integral is saying is the signed area under this line, which hopefully you didn't forget that we can also view this integral as the sum of the area, right? So you could either break it up into a triangle and a rectangle and find the area that way. But I feel like most students are comfortable with that. So I'm going to show them as a trapezoid, right? So the trapezoid is essentially the height of a trapezoid is the average between the upper height and the lower height. So the upper height in our case is 21 and the lower height is 12.5, right? And we need to take the average of that. And then the base is the exact same as before. So it's going to be 4 minus 0. So this comes out to 16.75 times a width of 4, which again, if you forget the excuse me, if you get the inverse power rule, you still end up with the fact that this is 6, 7, just by viewing this as a signed area under the curve. Okay, so let's look at this next question. So the next question is definitely more of a complicated definite integral, right? We have the integral from ln of 1 plus pi to 0, right? This integral of e to the x cosine of 1 minus e to the x dx. So I'm not seeing anything that I can really do off the bat, right? So I've got e to the x and I know what that is, but then it's multiplied by something. And remember, I'm going to make a note and I'm actually going to write it in red. There is no product or quotient rule for integrals. It would be really great if there was, but unfortunately, there is not. So we cannot just do like the integral of e to the x times the integral of cosine, right? But I am seeing a composite function. And if you remember from our U substitution lecture, typically if you see a composite function, you can do kind of U substitution, which is the opposite of chain rule, to get the answer, right? So if you're confused of what a composite function is, I'll briefly talk about it and I'll write it in blue over here, right? So a composite function is something that you can write as right? F times g of x, right? Where the argument of the outer function f of x is not just x, right? It's actually g of x. So we could also write this as, you know, I'll actually write it this way. So I can write for our example, if we have f of x as the outer function equals cosine of x, right? And then the inside then I need to be g of x, right? So then g of x is equal to 1 minus e to the x. We see that f of g of x actually equals cosine 1 minus e to the x, which gets us started. So since there's a composite function, we actually are going to assume that u equals the inside of the composite function, or in our case, g of x. So I'm going to write that u equals g of x, which in our case is 1 minus e to the x. And then I'm going to take the derivative. So we have du, and then the derivative of this, right? Derivative of 1 is going to be 0. Derivative of e to the x is going to be e to the x. So we have minus e to the x dx. But, so this is great because I see an e to the x and I see a dx, but we're off by a factor of minus 1, right? This negative sign here. So what we need to do to use u substitution is rewrite it so that we have du, the opposite of du, equals e to the x dx. And by doing this, now I can directly substitute everything in. Because this is a definite integral, though, we need to do one more step, and that step is the fact that these bounds are actually written in terms of x. So I'm going to denote that as like x equals this and x equals that. But that's not helpful because we need to go all in when it comes to u substitution. So everything needs to be written in terms of u. So what we're going to do is we're going to take the u that we've defined and rewrite these in this function, right? And figure out what u that corresponds to, right? So if we have u of ln of 1 plus pi, that then plugging that in equals 1 minus e to the ln of 1 plus pi. Using the fact that e and ln are inverse functions, this actually equals 1 minus the quantity 1 plus pi. And we distribute this negative sign to see that this actually equals negative pi. Okay, so the upper bound equals negative pi, and the lower bound, u of 0, well, that's just going to equal 1 minus e to the 0. E to the 0 you need to know is 1, so 1 minus 1, this just equals 0. So we can actually rewrite this whole integral down here as the integral from u equals 0 to u equals negative pi times, actually, I'm going to do this, cosine of, remember, we made u 1 minus e to the x, so we are going to put u there. And then we realized that this e to the x dx actually equals r minus du. So then again, this is just a minus 1, so we can pull that out because it's a constant. So then this is going to equal minus 0 minus pi of cosine of u du. And this should hopefully ring some bells for you. This is in fact one of the nice antiderivatives that we had on the U substitution day. And remember, if it's in a box on the worksheet, that means you can just memorize it, right? You don't have to necessarily understand why or where it comes from. That's what class was for, where we demonstrate why these make sense. But if it's in the box, you can just use it for the final with no justification. Okay, so cosine of U is going to be integrated to minus sine of u because we have this negative sign here. So remember, cosine goes to sine normally, but we have minus cosine, so it becomes minus sine, and we need to evaluate that at u equals minus pi and u equals 0. So we are going to do that here, where we know that this is going to be minus sine of pi minus negative sine of 0. So these are basic trig identities that we need to know. And in fact, we know that sine of pi is going to be 0. So this is minus 0, and this is minus negative, and then sine of 0 is also 0, right? So we're essentially subtracting 0 and adding 0. It doesn't matter. The answer equals 0. So we took this very complicated looking definite integral, and we realized that actually it does equal 0 overall, which is very nice. Okay, but I want to continue a little further with this, right? In fact, I want to look at the fact that what if, oh, I'm sorry, I see I have a chat. Give me a second. Is the first term sine of pi or sine of minus pi? Good point. It is sine of minus pi. Absolutely good call, but it doesn't matter because it still equals to 0. So thank you for that. But essentially, they're the same point. They differ by 2 pi. Okay, thank you for that. Okay, but now I want to look at what happens if we pick the wrong u, right? So I'm going to rewrite this integral, right? It was x equals 0 and x equals ln of 1 plus pi e to the x cosine of 1 minus e to the x dx, right? And let's say we understand that we're going to need u substitution for this, right? But we look at this and we say, oh, there's an e to the x here. And I know the derivative of e to the x is in fact e to the x, which is here. So what if I make my u equal to e to the x instead? And then we know that this is going to be du equals e to the x dx. Okay, so we can rewrite this interval or this integral, but we also need to change these bounds, right? So first we have u of ln of 1 plus pi is going to equal e to the ln of 1 plus pi. And again, e and ln are opposites of each other, so this just becomes 1 plus pi as our upper bound. And u of 0 is going to be e to the 0, which just equals 1. So rewriting this whole integral, we get the integral from 1 to 1 plus pi of, right? So now we have, remember, u equals e to the x. So we end up with cosine of 1 minus u. And then remember, du actually equals e to the x dx. So e to the x dx, right? We can write this just as du. So this almost looks like something we can solve. And if you remember, we talked about it briefly one day. It was an aside of this formula where we could rewrite it, the sum and difference formula of cosine. We would definitely never ask you to do that on an exam. So unless we give it to you, you will not have to have that memorized. So that probably is not going to be the way forward. But what is the way forward is now I can actually do another substitution, right? Where I want this to just become one value, right? So I want to make, I would love to have a cosine of something, and because I know that antiderivative, right? So I'm going to do another substitution, and I'm going to call this one W, let's say. W equals 1 minus U. Okay, and then if we wanted to stick with this color pattern, dW would then equal minus du, right? Because we're taking the derivative of this, right? This is a minus sign, so they're almost the same. Okay, and then we can rewrite the bounds in terms of W now. So we would have W of 1 plus pi is going to equal 1 minus 1 plus pi. That quantity, right? We distribute this. So it is going to equal minus pi. And then we have W of 1 is going to equal 1 minus 1, which equals 0. So at this point, let's write the integral, right? We have 0 to minus pi of cosine of W now. And then we need to multiply by this dw, or this, we need to get to dw, so we need to do minus dw, because if we go back up here, we have that minus dw equals du, and du is what we have. So then this becomes our integral, and then hopefully this is ringing some bells. This is looking familiar, right? So we're going to pull this out. So we have minus the integral from 0 to pi cosine of w dw, and we know how to solve this. In fact, it is going to equal minus sine of w evaluated at minus pi and 0. And this is exactly what we had before. So if I go back to this page before, we see that this is exactly the antiderivative that we had before. It's just in terms of w, not u. And this is hopefully a way to show you that even if you pick the wrong choice, if you pick a good enough guess for the u, you can still recover the same answer. It is just going to involve a few more steps. So another u substitution, and in our case, we had a w substitution. Um, but as always, it really is important to recognize composite functions, right? And realize that, oh, u should almost always be the inside of that composite function. So the full 1 minus e to the x, not just e to the x or minus e to the x, right? This full thing. But it doesn't matter because we can still recover the final answer. Um, and in fact, we can go here and see from previous computations that this equals 0. So we still get the same answer overall, which is very good. We just had to go a different way about it. Okay. Okay. Seeing no questions in the chat, I'm going to continue forward. And this, again, this is looks like a cosine of x times something that's cosine of sine of x, right? And since there is no product or quotient rule for integrals, I can't just take the integral of cosine of x and the integral of cosine of sine of x, right? But I'm seeing cosine of sine of x, so that probably tells me that there's a u somewhere, right? And in fact, if we let u equal sine of x, because that is the inside function in our composite function, cosine of sine of x, then we can try to use u substitution here and see what happens. So we end up with du is going to equal cosine of x dx. And remember, we're taking the derivative here, so that's why sine goes to cosine. Even though it is an integral problem, we are doing du here, and that's why we get cosine here, not minus cosine. Okay. And again, these bounds are in terms of x, but I'm going to, for demonstration purposes, keep them in terms of x, right? So I'll just denote that as cosine of x equals minus pi, x equals pi over 2, and then now we have cosine of u, because we made u sine of u, right? So we have cosine of u. And then dx, cosine x, we have that. In fact, that just equals du. Okay, again, this is a relatively straightforward antiderivative, and we know that this is going to lead us to sine of u, evaluated at x equals pi over 2 and x equals minus pi. And you might wonder why we can do this, right? Because I said early on we need to either go fully into U mode, where all of our bounds are in terms of U and our du, and we have a function of U here. Um, and absolutely that's really, really great. But if you forget that, right, we still know what U is. So we know that this just equals, right, sine of, oh, I want to make this blue, excuse me, sine of x, right? And then we can evaluate this. Now that this is a function of x, we can evaluate this at pi over 2 and minus pi. And we're going to end up with sine of pi over 2 minus sine of minus pi. Okay, so this is really going to check our trig knowledge here. So sine of pi over 2, we actually know that this equals 1. This equals 1 here. And, okay, excuse me if for some reason my screen sharing is no longer active. Give me just a second to fix that. Okay, so we're back in business. Right, so we know that sine of pi over 2, well, that's exactly equal to 1. So we have sine of 1 minus sine of minus pi. Minus pi, as we talked about before, we know that that's 0. So we end up with sine of 0. And then sine of 1, I don't know what that is, so I'm going to keep it as such. And then minus sine of 0, I know what that is. In fact, that's 0. So our final answer is actually going to be this sine of 1. Okay. And the reason I show you this way is the fact that it seems like there's an extra step, but as long as we know our bounds in terms of x, and we know u, and we need to plug it in back for x, right? This is a completely valid way of doing this. And we're going to do it kind of the more traditional way right now. But I just wanted to point that out, that this is another possible way. And if you keep track of the bounds, and if they're in terms of x or u, you are still able to get the right answer. As we'll see, sine of 1 is the correct answer for the other one as well. Okay, so that was one way to do it, and I'm gonna kind of write it this way, right? The only thing is, over here, I need to change these in terms of u, right? So if u is sine of x, we have u of pi over 2 equals sine of pi over 2, which equals 1. And then u of minus pi equals sine of minus pi, which equals, as we talked about, 0. So then if we want to fully write this integral in terms of u, right, we have the integral of cosine u du, and then our bounds are actually in terms of u. So we can do 1 and 0, and this antiderivative is well known to us, and in fact, we just used it over here. We know that this is going to be sine of u evaluated at 1 and 0. And I know since these are now in terms of u, I don't have to convert back or anything. I can just plug in, right? So this is going to equal sine of 1 minus sine of 0 by the second fundamental theorem of calculus, which just equals sine of 1. So as we see, we do end up with the exact same answer, whether we keep the bounds in terms of x or keep them in terms of u, or convert them in terms of u. Personally, I prefer this way. Um, I prefer this way of doing it, where we have kind of everything in terms of U because I'm just able to then directly plug in and I don't have to worry about converting again. Okay, so that is another question in the books. So now let's look at this one. And this one looks challenging, right? And my advice from earlier in terms of what a good U would be is not always going to be helpful here, right? Because immediately what I see is this is a composite function, right? So if we thought of it as a composite function, where the inside is going to be u equals 1 minus x squared, then we would have du equals minus 2x. And there's a 2x dx, excuse me. And there's a reason that this is not going to work, right? Because I don't have an x that I can get from the problem, right? I can move this minus 2 over, no problem. But in here, I don't have x dx, right? I have arc sine x dx. Um, so this is probably not the way to go about it. So I'm going to actually cross this out, not erase it because it was a good thought, but always when you're doing these problems, guess what you think a U is, and then from there try to figure out if that's actually it. And there really is, it should just work out kind of magically that everything in there becomes something that you care about and you can make it in terms of you. So one thing I am seeing though is arcsine of x, that is a hard function to get rid of. So I would hope that arcsine of x is either my u or some way related to my du. But, right, if I look at this and realize that this is arcsine of x times 1 over 1 minus x squared, all that in the square root, then I realize that I see not only a arc sine, I see the derivative of arc sine hiding there. So I'm going to let u equal arc sine of x. And then as I just pointed out, du is going to be 1 over the square root of 1 minus x squared dx. And again, this is one of those derivatives you're just going to need to know, both the derivative and the integrals. Um, okay, so this means that we can rewrite this function. I'll go back to black. This means that we can rewrite this function as the integral of u, because remember arcsine of x is u, and just to help us visualize that, I'm going to make it blue. U, and then we have 1 over square root of 1 minus x squared dx. Well, that is exactly what our du is. So I'm going to make that red. And so now we have the integral of u du, integral of u du. And this is just a simple inverse power rule, right? We could think of this as u to the first power, right? So then what we have is we have u to the 1 plus 1 over 1 plus 1, right? Because this 1 is the exponent. And then remember plus c, because this is the first indefinite integral. I kind of glossed over that, but this is an indefinite integral. Okay. So let's simplify this, right? So again, just to help us visualize, we're going to have u, and this is going to be u squared over 2 plus c, but I don't really care about u. I mean, u is useful for helping us solve this problem, but the question was posed in terms of x, right? So I actually want to go back to x, right? So that our answer is going to be arc sine of x, that quantity squared divided by 2 plus c. Okay. And one thing that I find is really helpful with indefinite problems, especially, is the fact that I can easily check my work, right? And I'm going to do that for us right now. So as I said, when we're doing these antiderivatives, if we take the derivative of the antiderivative, we should end up with the original integrand. So let's see if that is the case here. So derivative d dx of arc sine of x squared over 2, right, plus c. So as I mentioned, U substitution is kind of the inverse chain rule or the kind of anti-chain rule. So to take the derivative, we're probably going to need the chain rule involved. And I'm seeing if we consider um, the outside function as x squared and the inside function as arc sine of x, we can use the chain rule. So we end up with 2 arc sine of x over 2. And then we need to take the derivative dx of the inside, which is arc sine of x, right? And then the plus c goes away because it's a constant and we're taking the derivative with respect to x, right? So this is going to simplify, right? I see a 2 and a 1/2, so that goes away. So it becomes arc sine of x, and the derivative of arc sine is going to be 1 over square root of 1 minus x squared. And if we notice, right, if we put arcsine on top, we end up with exactly the integrand we started with. So this is a wonderful way to check our work. And we see that, yes, arcsine squared over 2 plus c is the correct antiderivative because when we take the derivative, we end up with the original function. Okay. Okay. So again, seeing no questions in the chat, we're going to keep going forward. Right? And now we have this here. Um, so our advice of composite functions, I see a composite function. So if I let u be the inside of this composite function, right? So u equals square root x, right? I might be tempted immediately to be like, oh, so it's going to be cosine of u over u, but then I still get a dx, right? And that's not really helpful because, like I said, there's no quotient rule for integrals. So having cosine of u over u is not really going to get us anywhere, right? And we still end up with a dx. So we need to continue this process. And the process is going to tell us that we take the derivative. So du equals. First, though, I'm going to realize that the square root of x is just equal to 1 or x to the 1/2 power, right? And that's going to help me identify the fact that this is a power rule. So I'm going to pull this down and go 1/2 x to the minus 1/2, right? 1/2 minus 1 is equal to minus 1/2. And hopefully you see by now, but if you don't, we have 1/2 1 over square root of x dx is our du. And that's good, right? Because I see a dx, I see a 1 over square root of x, right? So I'm almost there. The only thing I have is the fact that I have 1/2 of this, right? So I'm going to just rewrite this, right, as 2 du equals 1 over square root of x dx. And then because this is an indefinite integral, I do not have to worry about changing the bounds. There are no bounds to begin with, right? So then I'm going to rewrite this. So we have cosine of u du. And after u substitution, as I've said before, you should hopefully get something that you know how to take the antiderivative of. So cosine is one of those that we definitely know how to take the antiderivative of it. So we are going to do that now, right? So this is going to equal, I'm sorry, one thing I forgot, excuse me. We have a 2 here, right? So I need to substitute in that 2. So 2, which leaves us with 2 times the integral. And remember, cosine, excuse me, I'm taking the antiderivative, so I'm going to, right? So 2 times sine of u plus c because we know how to do cosine of u du. And again, we don't care about sine of u, we care about sine of x, right? So using our u substitution to get us back to x, we have 2 times sine square root of x plus c. And this hopefully is the correct answer, but we can also check our work to make sure of this. Okay, so if we do that, d dx of 2 times sine of square root of x plus c. Again, I'm seeing I'm going to need to use a chain rule, which makes sense because we used u substitution, right? So if I let the outside function be sine of x and the inside function be square root of x, we end up with 2 times cosine of square root of x times d dx square root of x, which then equals 2 cosine of x, and the derivative of this, as we've already talked about, is going to be 1/2 square root of x. So I see that these are going to cancel, and I end up with cosine of x, I'm sorry, cosine of square root of x divided by square root of x, which is exactly what we started with. So I know that this antiderivative is correct. Okay. And I think maybe we've dealt with this before today, maybe not, but this next question, we're definitely going to deal with this, right? So I'm seeing 2 different terms in our integral, right? And so one thing I just want to make it clear by the definite integral properties, and this is an indefinite integral, but it still works. This is going to equal, right? So if we have cosine of a plus b, right? That is the same as the integral. Let's do this in terms of x, right? The integral of a dx plus the integral of b dx, right? That we can separate different terms into different integrals, right? And that might make our job easier, because this integral is looking a little messy already. Okay, so I'm going to use this, and I see kind of 2 composite functions here, right? Um, I see kind of this one right here where we have cosine of x and the inner function is x squared plus 2. And then I see over here, um, we have kind of maybe a 1 over x and as the outer function, and then we have x squared plus 1 as the inner function, right? So I'm going to use the fact that x squared plus 1 happens in both of them, and they would be kind of like the inner function. And both, I'm going to use that to give us a hint that u equals x squared plus 1. And then from there, I'm going to do du equals 2x dx. Remember, the 1 goes away. It is a constant. But I don't have a 2x. In fact, I have just an x. So I'm going to rewrite this as du over 2 equals x dx. Excuse me. X dx. Okay. So let's see what sort of simplifying we can do now. So again, I have 2 terms, right? So I'm going to actually separate them into 2 terms, right? So the first one, I have an x dx, right? So that's du over 2, and then I have cosine of u. So putting that together, I have cosine of u, and then I have an x dx, which equals our du over 2. Right? And then the second integral is going to then be the integral of, well, since we said u is that, that looks like it's going to be 1 over u. And then we have an x dx here, which is exactly what we need to substitute in du over 2. So we're going to do that, du over 2. And then let's reflect real quick. We see cosine of u, du which is okay. We can do that. And then we have 1 over u du. And again, these are off by some factor, but that's a-okay. These are both antiderivatives that are well known to us. Okay, so we are going to then take the derivative, or I'm sorry, take the integral, right? And so we should end up with 1/2 sine of u plus ln of the absolute value, 1/2 times ln absolute value of u. Okay, u. And last but not least, we need to substitute these in because we don't care about u. So we have 1/2 sine of x squared plus 1 plus 1/2 ln of the absolute value of x squared plus 1.
Can I just ask a quick question? Sorry.
Yeah, you're totally okay.
For the 1 over u part of the integral, can we just show how the derivative canceled out? I'm just having trouble. Let me know if that made sense.
Um, I'm I'm confused what you mean by the derivative canceling out.
How we got rid of, how we knew that we could get rid of the x over, like where the x went. I know we substitute x squared plus 1, but the x on the top of the.
Yes, so the x on the top, it becomes part of the x dx. And we see that in the red du over 2 equals x dx. Um,
Okay, thank you.
Yeah, so that's why I someone asked in one of the sections where it's like, oh, to use U substitution, we need to force everything to work, and if it doesn't work, we need to find a different U. And I prefer to view it as like we need to just kind of guess and see what happens. And right, following this step where we have a U and then we do the du, we need to then rewrite it and see kind of what's left over, if anything's left over. And if nothing's left over, then U substitution is probably the best way that we can go forward.
Thank you so much.
No problem. Okay, and then one thing I forgot, which would lose you points, so please learn from my lesson, right? This is going to be, right, an indefinite integral, so we need our plus c in both of these steps. If we don't have that, remember we have this plus c because this is a family of functions that share the same derivative, right? So to indicate that is an entire family of functions and that there are infinitely many functions in this family that all differ by a constant, we need to write this plus c or else we will definitely lose points on the final exam. Okay, so I have a few more questions. This one looks very, very similar to the one we just did, but the difference is actually right here, right? This is used to be an x over x squared plus 1 in the last question, but now it's a 1 x squared plus 1. And I wanted to do this because of the fact I really wanted to hit home that we can do the integral of a sum is the same as the sum of the integrals, and realize that you can do U substitution on maybe one term, but not on the other, and that's completely okay, because when we separate them into separate integrals, we just need to solve them integral by integral. So to do this, right, I'm going to not really explain what I did because this first term is exactly what we did last time. So I'm going to write u equals x squared plus 1 and then go to du equals 2x dx and then divide by 2 to get the fact that du over 2 equals x dx, which is what we're going to need. Okay, so I'm going to rewrite this in terms of two different integrals, right? So then we have the cosine or the integral of x cosine of x squared plus 1 dx plus the integral of 1 over x squared plus 1 dx. And we see from this first one, I have an x dx, and I have a cosine of what we're going to call u, right? So I'm going to rewrite this first one as cosine of u du. And then this one, we might be tempted to realize that this is x squared plus 1, which is exactly what we made our u, right? And that, but then we would end up with 1 over u dx. And that would be kind of like trying to force something because not everything works out magically, right? It's not x dx anymore like we had last time. It's 1 dx, which is not going to help us. But hopefully, this should look familiar. This was on the list of well-known, in the box, the well-known antiderivatives. And in fact, this is just equal to arctan of x, right? This integral is just equal to arctan of x plus c. So we're actually not going to have to do u substitution on this one. As before, we did have to do u substitution here, so let's work that out, right? So this becomes sine of u plus arctan of x plus c. And remember this u is equal to x squared plus 1, right? So we end up with sine of x squared plus 1 plus arctan of x plus c. So I did this because it looks so similar to what we last did, the last problem. However, we can just break it up and understand antiderivatives and not have to do u substitution on both terms. So if we were on the exam to give you an integral that's a sum of multiple things, you can do them kind of independently, which I think is very helpful because then you can be more flexible with your integration techniques, right? And we did them separately because this we needed u substitution for, and then this we actually didn't need u substitution for. So we could be flexible in our approach. One uses u substitution, the other does not. Okay. So last but not least, I wanted to not forget our roots. So this question is very, very similar to kind of the first question where there is an underlying geometric interpretation, right? We can look at this definite integral as the signed area under the curve from 0 to a, right? And again, if we were to ask something like this, which requires some sort of trigonometric identity, cosine squared of x equals 1/2 cosine of 2x plus 1, right? We would give it to you exactly like we're giving it to you now, right? So hopefully this integrand, the square root of a squared minus x squared, looks familiar to you. And again, my apologies for the technical difficulties. I'm trying to get it back up. Okay, my apologies. It seems that my Zoom hates me and I had to leave, but hopefully I am back for good. Okay. So hopefully now you can see my screen, and I don't know where I left off, but I'm just going to start back with this problem where just like before, we had a kind of underlying geometric understanding where there was kind of a trapezoid or a rectangle and a triangle, if you prefer to view it that way. And there was a point where we had the signed area under the curve. And hopefully this formula, this a squared plus x or minus x squared square root, looks familiar to you. And in fact, it should, because this is the exact, I'm gonna go like this, right? This is the exact formula for a half circle, right? The upper half circle, in fact. And if this is 0 and this is a and this is minus a, this is also going to be a. What we're trying to do is look at this and figure out the area under the curve, the signed area under the curve, right? Which corresponds to this area. Okay. So from that perspective, this is very straightforward, right? This is just going to be a circle centered at the origin of radius a, and it's just going to go from 0 to a. Since this was the upper half, and we're only doing half of that, that's a quarter circle. So we have the answer is 1/4 a squared pi, or pi a squared, where a is the radius. But I think a fun thing that we're going to try to do now is how to use substitution in these trigonometric identities to prove this, right? So our underlying geometric intuition is helpful here. So hopefully you do this if we were to give you something like this on the exam, but if not, that is totally okay. So what we have here is this function, right? And I am going to do something kind of out of the ordinary. I'm going to try to pull out an a here, um, and see what happens, right? So then we have the integral from 0 to a of square root of a squared 1 minus x squared over a squared dx. And because this is now a product, right? I have a squared times 1 minus x squared over a squared. I can pull this out. So I have 0 to a square root of 1 minus x squared over a squared dx. Okay. So we're now going to do a u substitution. And as opposed to, kind of it being straightforward and making the problem simpler, what we have to do is make the problem slightly harder in the meantime, but it will make our lives easier in the long term, right? So I'm going to switch colors to u, and I have u equals, I'm going to do, oh, I'm sorry, the problem is in terms of this. So I'm going to do x equals a sine of t, okay? And then from this, we have dx equals a cosine of t dt. And this might not look helpful in the meantime, but let's continue going forward, right? So since this is a definite integral, let's do the changing bounds, right? So a equals, right? A is x here. A equals a sine of t, and we're going into t, right? The only way for this equation to make sense is if t equals pi over 2, right? Because sine of pi over 2 equals 1, and we need sine of t to equal 1 so that a equals a times 1, right? And then now we have 0 equals, right, a sine of t, and a is a positive number, so we can divide that. So we need sine of t to equal 0. And we know that if t equals 0, sine of t is going to equal 0. So we can rewrite this as the integral of pi over 2 and 0 of a squared square root of 1 minus sine squared t cosine of t dt, right? Where we're just using our u substitution. So let me make it clearer, right? This was sine squared of t in blue, and this is going to be red, cosine of t dt. So one of the things that we would expect you to is the fact that this 1 minus sine squared t, the square root of that, well, that's related to 1 equals sine of squared t plus cosine squared t. Right? This is often called the Pythagorean identity. DP, would you go through that in more detail? I don't know what that is.
Sorry, the last step, how did you get to 1 minus sine squared of t cosine t dt?
Good question. Good question. Thank you for that. So we know that, okay, I'm going to go here, right? I can rewrite this as x over a equals sine of t. And in fact, I have x over a squared here, right? Because x squared over a squared is the same as x over a, that quantity squared, right? So then because x over a equals sine t, I end up with 1 minus sine squared t. And then because we're doing a u substitution, this cosine t dt shows up, as well as this a here is coming out here as well. So that's why it's now a squared and not a. Really good question. Okay. Going back to this though, right? So what we're going to do is we're going to subtract sine squared of t on both sides to end up with cosine squared t. And then if we take the square root, right, we end up with exactly what we want. And then this, because of the fact that t is between 0 and pi over 2 here, which means that cosine is only positive, this just equals cosine of t. So the square root of cosine squared of t is just going to equal cosine of t. Okay. So this is really helpful because now what we can do is we can rewrite this integral as 0 pi over 2 a squared cosine squared of t dt. Okay. It would be super cool if we could do a u substitution here because I'm seeing if we have u as cosine of t, um, and then the outer function is x squared, it would be super great. But then remember we would need a sine of t somewhere, and we don't have access to that, right? But we do have this trigonometric identity that, handy dandy is given to us. So let's probably use that right now, right? So this equals the integral from 0 to pi over 2 a squared times 1 half cosine 2, I guess in our case, t plus 1 dt. Okay, I'm going to shift downward. And now we have a sum of two integrals. So what we are going to do is we are just going to find the antiderivative, right? So I'm going to pull out this a squared over 2, right? And then we have cosine of t squared, or cosine of 2t, excuse me. Well, that is just going to be sine of 2t. And kind of before the day before we discussed u substitution, we said that we could pull out a factor. So if we pull out a factor of minus 1/2, right? Because if we did the chain rule for this, the 2 would pull out and we would end up with the exact same thing, right? So that's exactly what we're doing. That's why this 1/2 shows up. And then what we're going to do is we're going to do 1 becomes t, and we're going to evaluate this, not the a squared plus 2 because it's a constant. We're going to evaluate this from pi over 2 to what was the lower bound? 0, right? Okay. So then we end up with a squared over 2, and then we have 1/2 sine of 2 pi over 2 plus pi over 2. Um, okay. And then we're going to subtract off where we evaluated at 0. And again, this is just an application of the second fundamental theorem of calculus. So we end up with 1/2 sine of 0 plus 0. And we're seeing that both of those are going to contribute nothing because sine of 0 equals 0. So what we end up with is we have a squared over 2 times 1/2 sine of pi plus pi over 2 minus 0. And sine of pi we know is going to equal 0. So this ends up being a squared over 2, 0 plus pi over 2, which means we have a squared pi over 4, which is exactly what we expected the answer to be because we know geometrically what it is. It's the quarter of a circle of radius a. So it's going to be pi a squared times 1/4. And we found out that our geometrical intuition and our calculus intuition will give us the same answer. Okay. That is all I prepared as the in-depth integration review. So just to cover this, we did a lot of U substitution. And the reason we put a lot of our effort on U substitution is the fact that if we can do U substitution correctly, we should hopefully end up with a function that's easy to take the antiderivative of. And that is giving us practice again with common antiderivatives and definite integrals and indefinite integrals. We also recalled our geometric intuition, where we could view things as, trapezoids, circles, squares, triangles, and the signed area under the curve interpretation of the integral, which was super helpful for us. And we also realized that if we have the integral of two functions, we could do the sum of two functions, to be clear. We can do the integral of one function plus the integral of the other function. And we can be more flexible with how we tackle each individual integral. So I will stick around for a little bit if there are any questions. But as I mentioned, that this is all I had prepared. Um, so hopefully this was very helpful for you. I'm happy to be reached via email. So my email is just going to be my first name, Mitchell dot Scott at emory.edu. Specifically, if you have questions about what I did here, and I will be posting these to the Canvas site as well as the recording. Yeah, good luck studying, everyone, and I hope you have a great time, and I hope your end of semester goes well and that you have time to enjoy yourself over winter break.
Scroll back,
I'm sorry, what was that?
you scroll back to the bottom of the prior problem.
The bottom of the prior problem.
Is there a missing 1/2 in front of the sign U at the bottom, next to the bottom?
There probably is, yes, because we have this du over 2 equals x dx. Yes, there should be a 1/2 here, a 1/2 here, and a 1/2 here. You are absolutely correct. I was trying to go quickly through that because we already saw kind of how that worked. And I think on the page prior, I did correctly put the 1/2. Yes. So good catch. Yes, it should be 1/2 sine x squared plus 1 plus arc sine x plus c.
Thank you.
Okay. Thank you for catching that. I'm going to stop the recording now.